midterm exam number um, 3, midterm exam number 3. More information will be shared. I did post an announcement this morning, all right, regarding the um, changes on SI Canvas page, the time slot, the hours. Please check and mark the new time schedule for support session. The SI session time slots have been changed recently. There was a survey. Please take note of that. I know you would need that for me time. If you need some help, please utilize those available resources for you. You will also need for final comprehensive exam, and the times have been changed. Other than that, if hopefully we'll get done with 8, I'll make also the quiz number 8 available so that you use to prepare forward for the upcoming exam. All right, yes, you have to go by what is given there, Jason. Go by what is given on the SI page. Recently, there were some changes, and I believe Nick will also allude to that, what the changes. Yes, Nick, I just say that that is the updated homepage. Thank you. Take note of that so that you don't show up at the times when no one is available. Other than that, let's just dive into chapter 8, where we stopped last time. We went as far as 8.3, covalent bonding. And this chapter and chapter 9, some texts they have it as a one chapter, covalent bonding. And basically the type of compounds we are looking at here is, or are those compounds made up of non-metals, all right? When we talk about the covalent, sometimes covalent compounds or molecular compounds, they do have covalent bonding. And this type of bonding involves sharing of electrons, all right? Sharing of electrons. So when we talk about covalent, bond, this is a bond formed as a result of sharing of what? Sharing of electrons, all right, in order that the atoms end up with 8 electrons. We talked about the octet rule, you will see that. So that if this is an atom, or the nucleus of an atom with, of course, protons, this is the nucleus of an atom, there is a force of attraction. They do share electron. These are shared electron. You have seen this before for hydrogen gas. We indicate the shared or the chemical bond by just line. We will see that when we write the Lewis structure for compound. So here is the sharing of electrons in terms of covalent bond. This is the type of bond which exists between two or more nonmetals, all right, to form a compound. We mentioned last time about the Lewis, G.N. Lewis, when we were going through the Lewis dot symbols for elements. Remember the elements where you had to draw the chemical symbol and the dots around it. We say the dot represent what? The dot represent the valence electron. So by now, I'm assuming that you are well versed with the periodic table, and we are looking at the top corner, the non-metals. Use the periodic table to predict the valence electron. For hydrogen, dot symbol, all right. For chlorine, all right, this is in group 7. You know how to draw the dot symbol. You don't pair them up until you go around. There is a 1 dot or lone electrons and pair. So the shared electrons in, all right, the shared electron is represented by a line, and we call those the we call it the covalent bond, sharing of electron. Could be single bond, we look at the double bond down the line. All right, we represent that using a line. All right, this is understood to represent a line, and we call this single bond, and it has two electrons. This is called double what? Double bond, and it has four electrons, and then this is triple bond, and it has six electrons. So that when you look at this line, it is understood that they are shared electron. When we talk about sharing of electrons, to form the or to end up with eight electrons. The exception for octet rule is hydrogen does not end up with eight electrons, but when it forms a chemical bond, it ends up with two, which is like helium. Helium is group 8, and the valence shell is filled up with the 2s when we talk about that. So next is, now, how do we draw the Lewis structure for molecules? The other one was Lewis structure for elements, all right? Just 10 elements and the dots around it. But how do we go about with the molecules? We can also draw Lewis structure for molecules, and there are two types of electrons here. We have lone pairs and the bonding pairs. Let me go back one slide more and use that to show you what is meant by bonding pair. This line right here is the bonding pair. This is the lone pairs. Any dots around the chemical symbol, all right, in a molecule, we call it the lone pair, shared electrons. So if you look at the number of electrons here, we have lone pairs, lone pairs, lone. This is bonding pair. This is shared electrons. The line represents two electrons. Look at my whiteboard. One line represents two electrons. We call that single bond. Down the line, you will see that there are molecules with double bonds, which means two lines. So here, when elements share their valence electrons, they either end up with two electrons for hydrogen, or eight electrons. We call the octet rule. To get the octet means 8. If you count the number of electrons on oxygen for water molecule, we have two here. That makes 4, plus the 4 electrons make 8. We call that octet rule. Likewise for what? Likewise for sodium, except for hydrogen, we do not end up with 8, but except 2. We call that duet rule. This means 2. So what we're going to do now is to draw the Lewis structure for molecules. How do we draw the Lewis structure for molecules? First, given the periodic table, you should predict the number of valence electron, and the group number represent the valence electron. We saw that last time. All right, we saw that last time. So how do we draw the Lewis structure? There are some sets of rules. All right, there are some guidelines you need to memorize, you need to learn, so that when you are given the chemical name or chemical formula, you should be able to excuse me, draw the Lewis structure for that, either polyatomic ion or a neutral molecule. I explained earlier on what is meant by double bond, what it represent, triple bond, how it look like. Nitrogen gas, we have triple bond, carbon dioxide, double bond, and this has to do with obeying the octet rule, when elements form compounds, they share their valence electron in such a way that they obey the octet rule, which means they end up with 8 electrons. Carbon, all right, has 4 valence electrons, form 4 bonds, all right. Nitrogen has 3 valence electrons and form. By the way, the single electrons tells you how many bonds it can form. For example, carbon, it can form 4 bonds. Let's see nitrogen. 1, 2, 3, 4, 5. If you look at nitrogen, there are 3, so it can form 3 bonds up to triple bond. Hydrogen has 1, so it can form 1 bond. Oxygen, if you draw the dot symbol for this, all right, you see that it has 2 single electrons. That's a guideline on how you know that how many bonds will be formed. So bottom line here is take home message from me is how does the double bond look like, triple bond look like compared to what single single bond. Once I get to walking you through how to draw the Lewis structure for molecules or polyatomic ions, you will see how double bond or triple bond will play out, will just come out automatically, that you don't have to memorize that, oh, I need to know that nitrogen gas has triple bond or carbon dioxide has double bond. There is no way you can memorize all elements with the double bond, all compounds, sorry, with the triple bond. It's just by playing with the rules so that you end up with either double or triple bond. Let's see, before we do that, there is a trend on the periodic table. There is a trend on the periodic table. This is a trend on the periodic table and is defined as electronegativity, is defined as the ability of an atom to attract electrons towards itself in a covalent. So when I say covalent bond, you know that this is a bond between two nonmetals, shared electron. This is a bond formed by sharing of electron. So the ability of an element to pull electron toward itself is called electronegativity. And there is a trend on what? There is a trend on the periodic table that this is the trend. It increases as you go from left to right on the periodic table. It what? Decreases as you go down the periodic table. So that if I give you 2 compounds such as hydrogen fluoride and hydrogen gas, even though both of them will have a single bond like that, all right, this will have a single bond like that, the sharing of electron is not equal based on what I just say here, electronegativity, which is the ability of an element to attract electron. And if you see the trend, if you see the trend on the periodic table, if hydrogen is on this side and fluorine on this side, the sharing of electron here is not equal. I can represent this that the shared electrons spend more time on closer to fluorine, as opposed to in this one there is equal sharing of electron. An equal sharing of electron leads to what we call bond polarity, that the bond is polar. This bond, this is polar what? Polar bond because of an equal sharing of electron. Fluorine is the most electronegative element on the periodic table. So I will, you may have seen delta negative and delta positive, which indicates on the molecule which portion of the molecule has electron rich, which portion of the molecule is electron poor. This is electron poor region of the molecule. This is electron rich portion of the molecule based on the position on the periodic table. This is more electronegative. This is the least electronegative. This one is, we call this non-polar bond, unequal or equal sharing. All right. Bond polarity is a measure of how unequal electron in a covalent are shared. So now what determines, instead of just saying that this is how does it play around, it has to do with the position of an element on the periodic table. So if you use this criteria, you can tell which portion of the molecule has high electron density compared to one portion based on the position on the periodic table. However, if there is equal sharing of electron for same elements, we say that the bond is non-polar, which means electrons are shared equally. They are shared equally. We can use electrostatic potential map to indicate. Sometimes we use the color coding to indicate which region has electron poor, electron rich region. The red indicates high density of electron, blue indicates low electron density. This to show you that color coding also sometimes can be used. So we call these non-polar bond. There is a polar bond here, and based on an equal sharing for this is complete transfer of electron. I don't want you to memorize the numbers here, all right? Linus Pauling, he was an American chemist, worked on determining the values you see on the periodic table. 4.0 for fluorine, which is the most electronegative element on the periodic table, and cesium here, all right? Maybe I can blow this up so that you can see the numbers I'm talking about. Fluorine with an electronegativity value of 4.0 is the most electronegative, and cesium here has the least on the periodic table with 0.7. What I want you to remember here, take home, is the trend on the periodic table. Moving from left to right, it increases. Moving from top to the bottom of the group, it decreases. Or if you are going up, of course, it will increase. Or if you are going back, it will decrease. What I want to show you here is we can use these values to determine whether the bond form is ionic. The difference in electronegativity values can tell us whether the bond is polar, non-polar, or if it is ionic. We will use these numbers I'm going to show you, and you will be given, all right? You don't need to memorize the numbers given. So apart from knowing the trend, you should be able to define this term, electronegativity. The trend, how it changes. So if I'm not given on this one, if I'm not given the electronegativity values, you have to eyeball where each one of these elements on the periodic table are, and then you will tell which one has the lowest electronegativity value. let's see, if I have my periodic table, and then I can just fill in on this, assuming that this is the periodic table. If I put silicon here, all right, if I put silicon here, just put it there. With respect to nitrogen, all right, nitrogen is above, somewhere there, above for silicon, and then gallium is on this side of the periodic table, and then cadmium, all right, is on this side of the periodic table, CD. I polling you can circle to answer a question similar to what you see here. You can just, circle on the periodic table to see which one has the lowest. And if I look at that, this will be the correct answer based on the position where they are. If you try to memorize, if you don't know what these chemical symbols stand for, chances are you will find it so hard to figure it out what you are looking for. And it's my expectation that you know the trend. This has to do with the trend, understanding the trend on the periodic table. Any question on this learning check? Any question? So in the exam, of course, you'll have the periodic table. All you need to know is that what is the trend? It could be the highest. If it is the highest, and then it is nitrogen. I've explained to you, the notation for showing the point polarity that we indicate with a partial charge or positive electron per region, and delta negative electron rich portion of the molecule where we have high electron. We say this bond is polar, this bond is polar. We're gonna use that to indicate the bond polarity. What I want to, let's see. Which one of the following contains the most polar? Tellurium, if I look at CF, fluorine is the most electronegative. Tellurium, there is, remember, sharing of electron. This is a metalloid, all right, nitrogen. If I look at this fluorine being the most electronegative, we are looking at the most polar bond. I can also use the trend here to indicate which one is the most polar based on the position. Remember, fluorine is the most electronegative, which will give us, the which will give us the most, the most polar bond based on their strength. Fluorine is the most electronegative, which means this compound, the first one, A, will have the most polar bond based on the position on electronegativity on the table. Uh, the difference, all right? The difference in electronegativity values, which you need to remember the range, can be used to determine whether the pole or the bond between two atoms is ionic, whether it is covalent, I mean polar covalent or non-polar, polar covalent or non-polar. If you look at here, electronegativity values, the difference, we indicate this as change in electronegativity. This means change in electronegativity. Change in electronegativity values. The values you see here, all right, tells us whether the bond is polar, non-polar. You will be given the electronegativity value for each element, Let's see. You don't need to memorize 1.9 or 0.9. The difference here is based on what you will be given. Either you will be given for each element. Let's see. If you look at this hydrogen fluoride, we have an electronegativity change in electronegativity value of 1.9. Where is 1.9 coming from? If we go back to, if I go back to this table right here, fluorine is 4.0 and hydrogen here is 2.1. So change in electronegativity is 4.0 minus 2.1, and that is where we have 1.9. That is how the that is where the 1.9 came from. It's from the electronegativity values we were given, the electronegativity values we were given in the table. So I don't need to remember. This is just using the equation, the higher, you may call this high, and then this one is low. The most electronegative minus the least electronegative to get the electronegativity value. This change in electronegativity value can be used to determine whether the bond is polar or non-polar. Given this is an example on how you can use the electronegativity values to tell which bond is polar, or the most polar electronegativity values. Given the electronegativity values below, which covalent single bond is polar? Of course, given here, the two elements using elimination method, this is non-polar. So B is non-polar. We rule out B. We wanted to see which one is polar. Nitrogen, so CH right here. If I have carbon 2.5 and 2.1. So change in electronegativity value here. Nitrogen, nitrogen. So this is 3.0. This is 3.0. And then the change here is 0, 0. 3.0 minus 3.0 is the same. So we make that 0.
I think that's supposed to be NH, not NN.
Oh, yeah, NH, yeah. So thank you. NH. So this is 2.1, and this one is what? 2.1. This is 0.9, correct? 3.0 minus 2.1. 2.1. This is A, this is B. Let's see, C is OH, all right, and 2.1, oxygen is 3.5, 1.4, D is O, C, this is 2.5, oxygen is 3.5, and this is 1.0, and E, we go to ON, ON 3.0 and 3.5. This is 0.5. So I'll look at the difference and see which one is polar or most polar electronegativity value. 0.4, 0.9, 1.0, 0.5. So if I look at this 0.5, 1.9, 1.0, I'm comparing these values right here, these values right here, this value right here. And based on this, this is non-polar. Polar, this is polar here. This is polar. This is polar, and this is also polar. This is the most polar, and based on this, I'll assume that which covalent single bond is polar, and 1.4 is the most polar in terms of the change in electronegativity. I guess this question has to do with the domains. 0.0, if change in electronegativity values, this is something you need to know. 0.4 to to 0.4, this is non-polar. And then 0.5 to 1.9, this is this is polar covalent. This is polar what? Polar covalent. And 2.0 or greater, all right, or and above, all right. Let's say this above this is this ionic bond. So if I want to know if the bond is non-polar, change in electronegativity between 0 to 0.4 non-polar, but if the domain lies within, we say that the bond is polar. 2 or above 2, the bond is ionic. And of course, you can use the metal and a non-metal. Of course, is also ionic, but given the values, I will just do the difference and see if the bond is polar. So for this, oxygen, hydrogen is the most polar single covalent bond, most single covalent bond. We can calculate, all right, we can calculate the net displacement of electron. Remember what we say, delta negative, delta positive, to indicate, we call that dipole moment, which indicates, all right, the displacement of electron in a covalent bond. It is measured in dpi. We use this note D for dpi. All right. Unit for measuring dipole moment when an equal electron. This Q is the charge, which is 1.6 times 10 to negative 19. I don't want us to get into details into that. What I want us to really get into is, the drawing the Lewis structure. I'm not going to get into the calculation of dipole moment. Let's just get to section 0.5, which is drawing the Lewis structure. Drawing the Lewis structure. This is critical for chapter 9. Writing the Lewis structure for molecules. Either you, all right, either you summarize in your own, all right, in your own words, section 8.5, the PowerPoint slide outline the steps. Step number 1, drawing. Let me just label this drawing Lewis. This is 8.5. Lewis for 1 molecules to polyatomic ions. Polyatomic ion. You can be given a polyatomic ion, that means it has an overall charge. Rule number 1 here, rules. And remember, you have to practice. You cannot read this. Practice is just like maths. You have to practice. I'll say fine. To what? Total number of what? Total number of valence electrons in a molecule or polyatomic ion. You have to find the total number. That is rule number 1. You need to know how many total valence, and I say total valence so that you use the periodic table to say how which group is this element. Figure out the valence electron. In this case, if I do have, if you look at the this phosphorus trichloride, phosphorus is in group 5, all right, and chlorine is in group 7. So this is where 7 is coming from. This is in group 7 times 3. We have 3, and we have total valence electrons. So once you figure it out, the total valence electron, check if it is polyatomic ion. Look at what you do with the anion. Add 1 electron for an ion. What does that mean? Let's say, for example, I do have a carbonate ion like that. I want to show you what you do with an overall charge. You will say carbon is in group 4, oxygen is in group 6, all right? We have 3 oxygen, so 3 times what? 6 for group 6. This is 18. And then if you add this, all right, this will give you 22. Because of this overall charge here, this is what we need to do. We add 2. We add 2 to give us 24 valence electron. This is rule number 1. How do you handle polyatomic ion with an overall charge of negative? Look here, if an ion add 1 electron for each negative charge, I'm adding 2 here because I have negative 2. So if it is for positive, I mean for here to there, and then you can do what? You can add 3. You'll add 3 for phosphate. If it is a cation, let's say ammonium, look at this, ammonium with an overall charge of negative positive 1. You will do this, N is in group 5, so that is 5. Nitrogen is in group 5. Each hydrogen has 1 valence electron. I'm multiplying it by 4. And this is 4. If I add, this will give me 9. Because of the overall charge of positive 1, I will subtract 1, and I have 8 valence what? 8 valence electrons. That is how you go about with an overall charge. Look at this. If a cation, you know, cation are positively charged. And we have few polyatomic cations. We have ammonium, hydronium ion, you subtract 1. So that is rule number 1 of finding the valence electron. I had to show you how you handle polyatomic ions. So for this, once you know the total valence electron you'll be working with, You now draw the skeleton. Number 2 here, draw molecule or polyatomic ion, skeleton of polyatomic ion, and always, unless otherwise, the first element is at the center, the central. This is what I mean by, the central atom, the connection. We call this external atom, external atom. It's not, I see in introduction to chemistry, somebody saying that you connect like this. No, 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 you don't do this kind of stuff. Always have a central atom, central atom, central atom, and you have to know that the least electronegative in this case goes at the center, of course, except for H2O. Now, once you have the skeleton of the molecule, rule number 3 here states that, I'm just making my own rule here. Look at 3 here. What we will gonna be doing, subtract bonding, subtract the bonding electrons from the total valence electrons. Remember in rule number 1, it's determine the total valence electrons. Subtract the bonding electrons from the total valence electron and distribute the remaining on the external atom, external atoms, such that octet, remember octet means 8, octet rule is obeyed, except hydrogen. Hydrogen does not end up with 8, it does not end up with 8 electrons. You may have an external atom being hydrogen. I don't want you to give hydrogen 8 electrons, does not need more than 2. So rule number 3 states that we need to find out how many bonding electrons we have used. Let me go back here. If you look at each connection here, we have 2 electrons here. In each line, we have 2 electrons here, we have 2 electrons here. In this molecule, we add 26. So if I do that, that means it will be 26 minus how many we have used here. If you look at this is 1, 2, 3. So we have used 6 electrons. So out of 6 electrons, all right, we subtract 6. We call this bonding. Let me abbreviate that or just write it, bonding electrons. We remain with 20 electrons remaining. Now, out of this remaining, based on rule number 3, we need to give it to the external atom such that the octet rule is obeyed. So I need to give each chlorine 6. The octet rule is obeyed by the first chlorine. So I've used 6 out of 20 remaining. 14 remaining. Let me give this 1, 2, 3, 4, 5, 6. I've used 12. 8 remaining. 1, 2, 3, 4, 5, 6. So I've used 6, 2 remaining. What will you do with the remaining? You give it to the central atom. Let me just erase this right here so that you see we end up with that. So that here, it's a connection. What remains now? These are the, these remain. Maybe I can use a different color here. This what remains at the end. Once the external atom satisfy the octet rule except hydrogen, the remaining electrons goes to the central atom. If you look at electron, total number of electron in the molecule of polyatomic ion, it should add up. So 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13. So I have 26 electron I started off with. I have 26 electron I started off with. So that's how you go about with polyatomic ion. There is a systematic rule. You have to start from here, go to this, go to this. Just like in chapter 4, when we were writing the net ionic equation, you had to balance the molecular equation. You come to total ionic equation before you derive what? Before you derive the net ionic equation. In a similar fashion, you need to know that rule number 1, I need to do rule number 1 before I come to rule number 2, before I go to 3, before I go to 4, because you cannot start from 4 and then you go to 2 and then you come to 3 and then you go to 1. There is a systematic approach on how you go about. Find the total number of valence electrons so that you don't memorize these. And next time I give you a different molecule, you'll get stuck and say, how do I go about with this? So this was rule number 2. I was saying draw the skeleton. And then you subtract the bonding electron. You may say, where is 6 coming from? It's based on the bonding electron. There are 2 electrons here, 2 electrons here, 2 electrons right there. That is what I had in my rule number 3 there. If you read rule number 3, subtract the bonding electron from the total valence. We had 26 minus 6. All right, we remain with 20. And remember, each line represents that. So what do? You satisfy the octet rule using the remaining electron. Make sure that the external atom satisfies the octet rule first before you work on the central atom. Let's see. That is what is happening here. That complete the octet rule. That means 8. You should have 8. So this one has 8. Remember, these are shared electrons. Phosphorus claimed the 2 electrons. Chlorine claimed the 2 electrons. So octet rule is satisfied by each chlorine right here. This remaining you have to place on, and they have to be paired. If you look at how I did, it should be paired. Whatever it remains has to be placed on the central atom. Central atom. Any question on that example? I want to show you where you have to generate a multiple point. Any question on that example? No question. This is maths. If you see there are some numbers we have to crunch. You don't read maths. You have to practice math. You need to practice this so that you get it right. I want to show you. All right. I want to show you an example where a double bond will be generated in order to satisfy the octet rule. You don't need to memorize that this molecule will have a double bond or triple bond. I will use, let's say, sulfur dioxide. Sulfur dioxide. And see how multiple bonds, you see this? Multiple bonds are necessary here. Sometimes it can be necessary, and I'm going to use this to show you how we generate a double bond. So for this, rule number 1 here, total number of valence electron is given by sulfur is in group 6, oxygen is in group 6, so 6 times 2, and this is 12. I'm finding the total number of valence electrons. So if I add up that, I'll end up with 18 valence what? 18 valence electrons. I don't need to work with more than 18. I don't need to work with more than 18. This is the maximum number of electrons I'll have. So for this, we draw, rule number 2, we draw the skeleton of the molecule. It's bonded to the central. You need to know which one is the central. Don't draw it linear like this. I don't want something like this. No, no, no. Once we have the skeleton of the molecule, subtract the bonding. So we add 18 minus what? Minus 4. We have used for this is bonding electron. Right here, these are bonding electrons with 14 electrons remaining. 14 electrons remaining. So next step is to satisfy the octet rule on the external atoms. All right. Octet rule. 1, 2, 3. I've used 6. So this is 8. We need to satisfy octet rule on the second oxygen minus 6, 2 remaining. These 2 remaining, we need to place on central atom, which is sulfur. You don't need to. I know some student might say, let me balance the equation and say maybe put there. It's look good, you know, I place around, and if I count, it's 18 total I started off with and I've ended up with. But sulfur always pair the electron, unless it is you know, odd number of electron. We will look at it later on the we will look at it later on the free radicals, the one with lone with odd number of electrons. So if you do the inspection on this molecule, you will notice that sulfur has 6 electrons. We have 2 here, we have 2 here, we have 2 here. 1, 2, 3. It does not satisfy the octet rule. But first oxygen, second oxygen, they satisfy the octet rule. In this case, this is where this, look at the PowerPoint slide. In this case, this is when it is now necessary to make a double bond or triple bond. You have to use use the electron pairs on the external atom to make a double bond, which in this case, you can either pick a pair from here or a pair from here. So if I make a pair here, I can get rid of 1 pair right there. And still, I do have 18 electrons. If you count 1, these are pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, which is the total 18 I started off with. If you look at the first oxygen, 1, 2, 3, 4, it is satisfied the octet rule. If you look at the central atom, which is now the sulfur, 1, 2, 3, 4, it satisfies the octet rule. And then this one is 1, 2, 3, 4. So in this case, we have, it is necessary to make a double bond. It is necessary to make a double bond.
So when you add that bond between oxygen and sulfur, would you not change the electrons or the valence electrons that are on sulfur to bond with oxygen, or would you just leave them there?
You just leave them there.
Okay.
Yeah, you just leave them there. So the key thing is satisfying the octet rule. This is a common mistake, which, you know, if you don't know, right, if you don't know what you are doing, you want to look it nice, somebody might say, let me just make another double bond here to balance the equation that this thing needs to be balanced. Yeah, it look good, but, you know, from the eye, you know, like it's pleasing to your eye, it's appealing, but you are breaking the laws here. If you look at now sulfur, 1, 2, 3, 4, 5, it has 10 electrons. No. You do not just leave that alone. Don't bring the 2 electrons from either. Common mistake, let me pack up. Common mistake I see also is, let's say from what we had before. We had this before, right? Before we generated the double bond. Somebody might say, all right, I think maybe the instructor forget to, let me just add some electrons so that sulfur octet the octet rule like 1, 2, 3, 4, 8, 11. If you count the number of electrons, you are adding 2 extra. We should end up with 18, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, somebody generated an extra electron. So be careful on generating the double bond or triple bond, for example. So in this case, it was necessary to generate a double bond. I will show you. Any question before I show you the triple bond? So the only way you will know that I need to generate a multiple bond is when the central atom does not satisfy the octet rule, or when each atom in the molecule, not necessarily central, does not satisfy the octet rule, with the exception, of course, of hydrogen. Let's see the nitrogen gas. Even though this one doesn't have a central atom, we'll see how we play around with this until we end up with a multiple bond. So nitrogen is in group 5, so 5 times 2, all right. We know we have 10. So the connection, you see that we don't have a central atom. We have used 2, so let's subtract 2. How many remaining? 8. All right. Group 5 is 2, 10. It's 2, 8 remaining. So if I keep 4 here, we have used 8. Nothing remains. But each atom does not satisfy the octet rule. Remember, the exception of the octet rule was hydrogen. So what do I do with, or what do we do with this? In this case, you can make a double bond here and get rid of that. If I count this, 1, 2, 3, this nitrogen has 6 electrons. 1, 2, 3, 4. The second nitrogen has 8, but the first one does not satisfy. So I will use electrons on the second, or from the second, and then get rid of that. If you look at first nitrogen and second nitrogen, 1, 2, 3, each one of them has 8 electrons the way it is. So it's just playing around with the octet rule, that it satisfies the octet rule. This is when it is necessary to form a what? A multiple bond. For polyatomic ion, all right, such as carbonate, I know I used this before. Let's use this before. I used this before. What do you do? There's an extra thing you need to do when dealing with polyatomic ion. Carbon is in group 4. Oxygen is in group 6 times 3. This is 18 plus 2. All right, let's add that. That is 22 plus 2. This is 24 valence electron, 24 valence electron. So we are working with 24. I'm looking at rule number 1. Carbon is bonded to 3 oxygen. We subtract 6. Let's subtract 6. 24 minus 6 remain what? 18. So in each one of them, we give what? Each oxygen is given 6 electrons. 6 electrons. 18 minus 18 remains 0. So we don't have what? We don't have extra electrons to give carbon, which is the central atom in this case, to satisfy the octet rule. No more electrons. So what do? You can either make a double bond here, you can either make a double bond here, you can either make a double bond here. So if I use the first oxygen, electron from the first oxygen, I've used the 2 electrons from the first oxygen to make a double bond here. And carbon, 1, 2, 3, 4, satisfy the octet rule. You do not leave for polyatomic ions, whether positive, I mean cation or anions. Since there was an overall charge of negative, you use a big parenthesis like that, and then put an overall charge of -2 there, that there was some 2 extra electrons. That's what you do when you are dealing with polyatomic ion. That if it is an overall charge of -3, you cannot put -3. If it is an overall charge of -1, you put a -1. So that's how you do the polyatomic ion. I want you to know that you don't live just the way we do with the neutral molecules. Polyatomic ions, parentheses. So next time you see that there is a big parenthesis, is because of what? Polyatomic ion. And now you may be given in the exam or in the quiz the chemical name, such as nitrate. You know, they expect you that you know the chemical formula for nitrate, all right? Nitrogen dioxide. If somebody works with that, you are working with nitrogen trioxide. But if you have an overall charge of negative, that is nitrate ion, just to give you that. Sometimes you may be given the name without the chemical formula for that case. So I've walked you through on how to generate the multiple bond. This is hydrogen cyanide, all right? You see the arrows point where we are taking the electrons, For most, all right, for most questions in this section is determining, you know, the total valence electron in polyatomic ion. That is rule number 1. For example, here, the ion ICl has dash valence electron. So if I do have that 7, I don't know if that will work. So 7 plus 1 is C I, or something is missing here. C the ion I has how many valence electron? (34, 35, 36, 28, 8. I need to check this compound here based on what we have. This is chloride. And iodine is in group 7. Yeah, they must have been a chemical formula here. I don't see how this could make. I'll check this, make sure that the chemical formula for the ion here. So if we add an ion, we'll have to add -1. But when I look at the multiple choice here, unless the choices are wrong, we could have used 7. Because if I look at this, it's iodine or I and chloride. I'll let you know this next time what we look based on the multiple choice. It does not support or even the chemical formula here for polyatomic ion. So remember, valence electron, you'll be given the periodic table. I think we went through this. Yeah, I've gone through this, writing that. It's the same thing. Identify the compound with ionic bonding. Of course, the one with the metal and a non-metal. Lithium bromide. This is just an element. This is a covalent, molecular compound.
I'm sorry, what was the answer to the last one?
The last one we don't have. Let me check this one. The last one I need to check the. Chemical formula for this, because if you look at iodine, what the ion ICL, I don't know if this is a capital I. None of the answers. This is what I say. I'll get back with you because it doesn't support. If you look at the multiple choice, I need to check whether this is the correct formula or the multiple choice were meant for a different question. So none of them support the question, all right? It's a defective question the way it stands right now. It should have been 15, but I'll check to make sure that the ion is correct. And at the same time, the multiple choice is supports what we are looking for. But if I were you, I'll just look at the periodic table and say, this is iodine, all right? Plus, which group is this? Which group is that? This is group 7 if it is iodine, and then group 7 for chlorine gives you what? 14, that is what I have here, plus 1 overall charge of -1 to give you 15, which is none of the answers here is Lawrence says supposed to be 15, but as I say, I'll go back and look on the, where I got this question, make sure that nothing is defective, but given in the exam, use the periodic table, the group number will tell you the valence electron. If there's an overall charge of negative, you add extra electron based on the overall charge. In this overall charge of -1, we add 1 here. If it is overall charge of -2, we have 2 electrons. If it is overall charge of positive, we subtract. Does that make sense?
Yes, thank you.
All right. Now, when Lewis structures for molecules are drawn, there are sometimes more than one possible structure. And they are all what? They are all correct. They are all satisfied the octet rule. But one is the most accurate or the most acceptable Lewis structure for that. In this case, when we are looking at what we call resonance structures are structures of the same molecule, but having different position of the double bond. We use what we call formal charge to determine which one is the most acceptable Lewis structure. And a formal charge is just like an electron giving in a molecule or a number assigned to. A formal charge is a number assigned to an element in a molecule. And once you assign each atom in a molecule the formal charge, which is totally different from the oxidation state. No, it is not the same as the overall charge based on the group number. Formal charge is calculated based on the Lewis structure. It is not something based on the periodic table that, okay, it is in group 1, so it is +1. It is in group 7. No. You have to do the formal charge. First of all, formal charge is given by valence electron minus minus non-bonding electron minus a half bonding electron. I've just rewritten this equation on bullet point where you see on the PowerPoint slide, the formal charge, which is Fc on my whiteboard, is given by the valence electron for that element, which you now use on the periodic table that use the group number to find the valence, minus a half bonding electrons, which I do have it right here, minus all non-bonding electrons. It's the same thing as minus. I like starting with non-bonding minus half. It's the same thing. Now, if you look at these two structures for carbon dioxide, each element satisfy the octet rule. Always, carbon can form double bond, single bond, even triple bond, the way we have it here. But if you look at the formal charges here, the higher the numbers on the formal charge, the least that structure is acceptable. In this case, for carbon dioxide, this is the most plausible structure on for drawing that. And the zeros you see here, they were obtained from this equation. Let's pick up the first oxygen and see how zero is obtained, how we end up with zero. So look at how I'm doing on my whiteboard. That oxygen is in group 6, all right? Oxygen is in group 6, so valence electrons is 6, that is where I'm getting 6. Minus, if you look at non-bonding, NP on my formula here on the whiteboard, NP non-bonding electrons. Non-bonding electrons. Non-bonding electrons here is 1, 2, 3, 4. Let's see, minus 4, all right? 4 electrons, 1, 2, 3. Minus a half of what? A half of bonding. How many bonding electrons here? 1, 2, 3, 4. Remember, 2 lines represent 4 electrons. So that we say 6 minus 4 minus 2. So this is the same as 6 minus 6, which is 0. This is where the 0 is coming here. This is where the 0, it's based on this equation. I don't know if you want to use the one given here or you will want to go with this. Valence electrons minus non-bonding electron minus half bonding electrons. So if I look at carbon, for the first compound here, it is 4 minus 0. I don't see non-bonding electron on carbon, so I put it 0. Minus a half of, you have now to look at what? The bonding electron on carbon. We have to 4 on this side and 4 on that side. So 8 minus half of what? 8. This is 4 minus 4, which is 0. That is where 0 is coming from here. You do the same thing for this oxygen. The way we did on the first one, it turns out to be 0. If you look at this, on the second structure, the first oxygen here, you say 6 is the valence electron, minus non-bonding, 1, 2, 3. So I have 6 non-bonding electrons minus a half of what? The bonding here is, there's a 1 line here, there's 1 line here, so a half of 2. 6 minus 1. That is where we have minus what? We have minus 1. This is where minus 1 is coming from. If you do the same thing for second oxygen, you'll end up with positive 1, you end up with this 0. So the formal charge is used when you have, it is used to determine the most acceptable Lewis structure for either polyatomic ion or a molecule. Question in the exam is, what is the formal charge of nitrogen, for example, or oxygen, for example, in the given compound, so that you know why we are doing this. We have just looked at the Lewis structure, and sometimes there are more than one possible structure, and formal charges are used in determining the most appropriate. For example, here, if you look at these structures right here, all of them are acceptable. We will rule out this, all right, because of the high numbers of what? Formal charges, high number of formal charges. But the dominant Lewis structure now, all right, if you look at this, you may say, which one is which? I see that they both have -1, -1, 2 zeros. Which one should I throw away? The one with, all right, the one with a negative charge on the most electronegative is the most plausible structure. So if I look at the sulfur, if I compare sulfur and nitrogen, nitrogen is more electronegative. This is above sulfur. Sulfur is below nitrogen. Nitrogen is above sulfur. So this is the most electronegative, and it takes, all right, formal charge with a negative charge on the most electronegative. See here, put a negative formal charge on the most electronegative atom. This one is least. So we take this as the most plausible structure for this Lewis structure. So let's see. Here is an example, or you'll see in exam, either you are given the structure or given the name. This is nitrate. You should be able by now to draw the Lewis structure for polyatomic ions. And remember, this is overall charge. So if we are looking for nitrogen, in this case, nitrogen is formal charge is given by valence electrons minus non-bonding electrons minus a half bonding electrons. So 5, because it is in group 5 for nitrogen, minus non-bonding, which is 0. I don't see any dots on nitrogen. I'm just sitting right here. We are on the nitrogen right now. I don't see any dots on nitrogen. That is why I have 0. That's why I have 0 here. No non-bonding electrons on nitrogen. Minus a half bonding electrons. So you now have to look at the lines. One line, 2 electrons, another line makes it 4 electrons, and then there are 4 electrons here, minus a half of what? A half of 8. This is 5 minus 4, all right, which is positive 1, which is positive 1. So you have to do the math.
For the previous question, where you were determining the negative formal charge on the most electronegative, my only question is just between nitrogen and sulfur. Sometimes I run into this just whenever you're looking at the periodic table and they're so close to one another. How would you determine that nitrogen would be more electronegative than sulfur by just looking at it?
All right, if you look at periodic table, nitrogen is somewhere here, and then sulfur is somewhere there. If you look at your periodic table, do you see what I'm talking about? Without looking at the numbers. So remember the trend on electronegativity. What has happened when you go down?
When you go down, it decreases, and then whenever you go left to right, it increases.
So if I look at it, I'm going down, that nitrogen is above sulfur in this case, and nitrogen will be more electronegative.
So even though sulfur is slightly more to the right, nitrogen's still going to overpower that?
But it is below.
Okay, so it's not really worrying about that then?
No.
Okay.
Yeah. because unless they were on the same, you know, like on the same line is now when you will talk about that. But you have gone down, which decrease, which compromise.
Okay, so then I guess whenever you're looking at it, would it be safe to say that we could go by group number first and then, or I'm sorry, period number and then group number when we're kind of looking at that?
Yes.
Okay.
Because at the top, you know, as you go down, you know, you look at the group number where they are. All right. I'll use that and say that, you know, as you go down, the electronegativity decreases. So sulfur has is less electronegative, going by that. Even if you go, let's see. Even if you go, there was a table right here. Where was it? Oh yeah, right here. I don't know if this will help. Look at that. So if you have here nitrogen, and if you look at the sulfur, where is sulfur? Right here, it's coming down. You have gone down. Even though you are at the right, by the fact that you are coming down, it compromises or reduces the electronegativity value. So you have to note the trend when you go down. If we were just going across and then things will change. You see what I mean? If they were on the same period.
Okay.
I know your concern was I'm going towards right, and I know when I go to right, it increases, correct?
Yes.
But you have to come down. You have to come down fast, which compromises that. It changes. But if you are going just linear without coming down, and then you'll say that sulfur, if sulfur was on the right side of nitrogen, which let's assume it was somewhere here in place of oxygen.
So I had a similar question, which is, I mean, essentially is like, how do you weigh if it's more important to go across a period or down? So like, for example, if you were comparing boron with chlorine,
if you are comparing boron with chlorine right here, right?
Right, or even boron with sulfur or phosphorus, it's like, yeah, you're going down, but you're also going two across. And so I guess the question more like the overall question is like, how do you know in a series of elements to weigh, are you going across the period or down a group, which is more important in ordering them without having the table in front of you?
Without going to table as you go, if you look at the, let's say for you pick boron right here and chlorine on this side and say which one is more, this will call for, I know you have picked this and that, this will call for giving you the actual molecule which will form a chemical bond. In this case, when you are comparing chlorine and boron, such cases, it may not really exist. It's just like saying that there is a covalent bond between sodium and chlorine, which is not the case. That where
so the question came from, like, I took the chapter 7 quiz yesterday, and there were some where it would just pick like random, you know, 3 random on different different areas of the period and in different groups. And without looking at the table, I'm like, okay, like how do I compare, let's say, like barium, chromium, and phosphorus? It's like, well, I don't know. I guess just, does it depend on which what's the word, which attribute we're talking about, whether it's more important to go up and down a group versus across a period? Because like sometimes in the quiz it would just give us like 3 random ones all across the table and be like, which one's more, you know, has a higher electron affinity? And it's like, well, within a group or within a period, the trends are really obvious. But if you're going across groups and periods, some of them it's not as explicit as where it would fall as compared to everything else. And so that was kind of confusing in the quiz.
Yeah, unless there is a specific question I need to look at, these are based on where they lie on the periodic table. I will eyeball and say that on this portion, it will be more electronegative compared to maybe on this side. And of course, you have also to align on the row, on the period, that if they are on the same row or if they are not on the same row, maybe you are just coming down and then again go on this side, and then it's getting more and more on in terms of electronegativity.
All right, I'm gonna try and set up a session with you to go over the Chapter 7 quiz because I think there are a couple specific questions where I was particularly confused.
Yeah,
But I'll do that outside of class.
all right, that will help because I don't want the exact same question or similar question coming in the exam and you missed it. Likewise to everybody else, if you have specific, if you can send me an email, if you don't have time to schedule one-on-one, that will be great. So for that, I'll use the general trend and say where is. For that, Lauren was asking about the nitrogen and sulfur, that if I come down, this will override, it will compromise. And the way I've seen is, if you look at, all right, if this is sulfur right here, and nitrogen is above, you have to look at where, when you come down, the electronegativity decreases compared to when you have nitrogen, which is above sulfur in this case, even though this is more towards the right on the periodic table, but it is below. And of course, other factors which plays a role here in terms of is it a metal or a non-metal. And in this case, for electronegativity values, most for ionic compounds, as we are looking at, that's just for covalent, which are non-metals, which will lie here, except maybe for hydrogen once in a while. But for most compounds we look at, they are the non-metals, the molecular compounds, which do share what? They do share electron. You will not see a metal and a non-metal because there is complete transfer of electrons, and we cannot talk about sharing and electronegativity in that case because of the complete sharing of electron. So this was the one on electronegativity. How you change that? So we place on the most, and I'll use the periodic. All right, I'll use the periodic trend. How does it change as we move from left to right? So, yeah, just send me an email whenever you are ready, and then I'll help you with the quiz. For next exam, it will be, you may see similar questions. So for this learning check, we found out that the correct answer in this one is +1, which is C, calculating the formal charge. I may give you, or you may be given the chemical name of polyatomic ion or chemical formula. So please go back to chapter 2, I believe, chemical formula for polyatomic ion, so that you know how to draw the Lewis structure. Well, I don't want to get in details into that. What I want to just mention on this, all right, resonance structure, I've explained to you the reason why we calculate formal charges for atoms in a molecule or polyatomic ion is so that to determine the most plausible structure when you have resonance structure. Resonance structures are structures of the same molecules having different position of either double bond or triple bond. Here is ozone. A double bond can be on this side, a double bond can be on this side. We use a double arrow to indicate resonance structure. We saw earlier on this structure, all right? There was a double bond there. We use resonance, we show resonance structure using this symbol, double-headed arrow, and the double bond can be on either side. And if I indicate, of course, all right, lone pairs of electrons, 6, 6, 6, and then to 2, And then the fourth, that a double bond can be on either side. A molecule can have three Lewis structure, all right? Or can have, we use these resonance structure arrows. Carbon dioxide, carbonate, a double bond can be on this side real quick. It can be on this side. A double bond can be on this side, or a double bond can be on this side of the molecule. What I want you to see is these arrows indicate resonance structures. All these are possible resonance structure. It's just moving around either double bond or triple bond, double bond or triple bond. Nitrate is an example. If you look at the double bond, it can be on this oxygen, it can be on this oxygen, it can be on that oxygen. And the double arrows here indicate the resonance structures. How many resonance structures can be drawn from? This will just call for using the Lewis structure, all right? Learning how to draw the Lewis structure, and I use this. These are possible of two structures. There's no way if you change, you're gonna go back. So correct answer for this is B, two possible resonance structure. For carbonate, three possible resonance structures. And the difference between all these has to do with moving around the multiple bond. To wrap up chapter 8, there are exceptions of octet rule. Whenever you draw the Lewis structure, there are some exceptions where the octet rule is not obeyed and it's acceptable Lewis structure. This is when you are dealing with free radicals. Free radicals are those ions with lone pairs, or I mean with single electron or unpaired electron. When there is odd number of electrons, we'll see that that's an exception of the octet rule. That is no way you can satisfy octet rule when you have odd numbers of electrons. When a molecule has less than octet, for example, boron will form 3 bonds using the single 3 valence electron and still be able to, be stable without necessarily ending with 8 electrons. And then elements, all right, in row 3 and below have extended. Molecules with more than 8 valence expanded octet. When we say expanded octet, is elements on row 3 and below can have expanded octet rule because of the 3 d sublevels. Remember, these sublevels take a maximum of 10 electrons. For example, if we have phosphorus pentachloride, you see, such molecules do exist. And if you are to draw the Lewis structure, you'll have 5 chlorines hooked up to the central atom. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 10 electrons on the central atom, which means there is an expanded what? Expanded octet rule. These are the exception of octet rule. It will just play out wherever you draw. So number 1, nitrogen monoxide, there is no way you can satisfy the octet rule in all the atoms in the molecule because it is unstable. This is what causes oxidative stress. Poron has less than 8. This is the dominant, and if you look at it, I gave you example. This is a staple. It has 6 electrons. It does not satisfy the octet rule. The most common, all right, the most common element or compound you'll see has those compounds formed with poron. It has fewer than 8. And for the expanded, all right, for the expanded one with more than 1/8, if a compound contain a central atom on row 3 and below, all right, it has a 3D sublevels which can accommodate more than one charge. And looking at the 2 structures here, formal charges have been assigned so that, you know, you tell which one is the most plausible. The most important thing here is expanded. So period 3, for any element on row 3 and below, it has an expanded what? Expanded octet rule. They are said to be hypervalent. And always, you know, you can just add even more electron on the fluorine to for fluoride on the central atom for that case. So the row 3 and below, you can have more than that. Of the following, dash cannot accommodate more than an octet rule. If I look at this, they were just, it's just a question of looking at which, when you write the electron configuration, which one has a D. If it has a D sublevel in its electron configuration, that means it has an expanded octet rule. It can take more than 8. And among the multiple choice I do have here, beryllium is number, beryllium Pe is number 4, row 2, and it cannot accommodate more than the octet rule. So what these has a D sublevels, nickel, scandium, osmium, and antimony. All right, they can have expanded. So I'll just pick C. This has, or this is in row 2. Anything on row 3 and below, they are all on row 3. Nickel, scandium, osmium, and antimony means they have expanded octet rule. The correct answer for this is C, Be for beryllium. Be for beryllium. Now, lastly, oh yeah, it's it's now 12:30. I'll stop here. Maybe just cover it next time. Please, the exam will cover up to 8.7. I don't want to continue beyond 12 or 30. I guess exam will cover, I want to give you 1 week to study. It will cover up to chapter 8. I will send more question. If there is no more question, I would like to stop sharing my screen. Thank you for tuning in. I'll see you again on Thursday. The class is ended. Thank you for tuning in. Have a great afternoon. The class is dismissed. Thank you.